Okay, so welcome everyone. Our next speaker is Jordan Cotler from Harvard, and today he'll be telling us about renormalization group flow as optimal transport. So without further ado, take it away. And as always, if you've got questions, we're not super strict, so interrupt or just drop a note in the chat, and I'll try to, or raise your hand, and I'll try to keep track.
Perfect. Yeah, of course. Feel free to ask throughout. So I'm going to tell you about some recent work that was just put on the archive last night in collaboration with Simon Rezchikov, who is a postdoc in mathematics here at Harvard. And again, the subject is renormalization group flow as optimal transport. And we'll talk about what optimal transport is and what in particular I mean by renormalization group flow and how they connect with one another. So let's begin with just a brief discussion about renormalization group flow. So the question which this tries to address is, how does our effective description of a physical system change as we tune the precision of our measurement apparatus? Now there's this whole subject of Rg flow, which is one of the central engines of quantum field theory, as well as statistical field theory. And in the context of work in this audience, it's also essential to our understanding of holography and emergent dimensions in holography. Nonetheless, something which I think is lacking, or that we can have a better understanding of, is what does renormalization group flow really mean from a computational or an information theoretic point of view? The goal of this talk is going to be to provide what I believe is a very compelling perspective or a partial answer to this question here of understanding a computational information theoretic perspective of Rg flow, which brings in tools in mathematics that have not conventionally, at least so far, entered high energy physics. So let me give the basic setup so that we can state the result and orient ourselves as to what we're going to be discussing. So for simplicity, let's consider Euclidean scalar field theory on Rd. So that is, we have a scalar field, which is a map from Rd to R. And in the Euclidean setting, we can package the data of our theory as a probability functional P sub lambda of phi, where lambda is going to be our cutoff scale. And this is proportional to e to the minus action, where the action will depend on the cutoff scale. So this is the effective action at some scale lambda. Now the Rg scale, or rather, maybe I should say the cutoff scale, where we'll do the cutoff, is some momentum cutoff lambda, which corresponds to a position cutoff, which is inverse to lambda, like call it 1 over L. Now, an exact renormalization group flow equation is a particular way of conceiving of Rg flow, which is fundamentally non-perturbative. We can think about an ERG flow equation as looking at a derivative with respect to P of lambda, namely a logarithmic derivative with respect to scale. So we change the scale a little bit. And on the right-hand side, we are going to have a differential equation in terms of functional derivatives of phi, usually up to its first two derivatives, in a manner which is going to be spatially local. And the idea is that there is going to be an exact way, given a non-perturbative Rg scheme, in which the probability function will change with respect to scale in a way that's going to be captured on the right-hand side by its functional derivatives. And I'll give some explicit examples of this later on, but the choice of Rg scheme is going to be encoded in the choice of this function f. Now, the idea of an exact renormalization group scheme is that we can think about it as a non-perturbative enhancement or generalization of our usual perturbative Rg schemes, Wilsonian Rg or otherwise. So these non-perturbative completions can have interesting formal properties that can be computed via the path integral, although in practice, if one wants to compute them in interacting theories, we are forced to do perturbation theory as we change the scale by a little bit. But nonetheless, for numerical applications, it's very nice to have a non-perturbative definition of what we mean by Rg flow, as well as for looking at more formal properties like Rg monotones. Now, this formulation, these exact renormalization group type equations go back all the way to Wilson as well as to Kogut, and were really refined by Polchinski in his beautiful paper in '84. Often one of the most famous examples of exact renormalization group flow is referred to as the Polchinski equation. Now, the result of this talk is that the exact renormalization group flow equations for an enormous class of ERG equations can be cast in the following very interesting form. So let's unpack what this means. On the right-hand side of this equation, this is a gradient with respect to what's called the Wasserstein 2 metric, which we'll talk about in detail. This is a certain metric on the space of probability functionals, or rather the tangent space to probability functionals, which captures data about what's called optimal transport, a very rich subject in mathematics. which I'll provide a review of in a few slides. This S is a relative entropy between our functional of interest or probability functional of interest P sub lambda and a background distribution Q sub lambda. This Q sub lambda, which we can think of as our prior distribution, we can regard as giving us our choice of Rg scheme. Again, we'll talk all these things more in detail. I just want to set the scene. The basic statement which we will make about this equation is that the renormalization group flow is equivalent to an optimal transport gradient flow. That the way in which we change the probability functional with respect to scale is equal to a gradient on the space of probability functionals of a relative entropy. This will have interesting applications for our understanding of Rg flow, as well as various properties thereof.
Jordan?
Yes.
Just to orient myself, this relative entropy is a classical relative entropy or a quantum relative entropy?
It's a classical relative entropy. Maybe at the end of the talk, I'm going to mostly focus on the classical setting or the statistical Euclidean field theory, but I can also make some comments at the end of the talk as to what you would want to do for a version of this with quantum states.
So you're just thinking of classical probabilities, the Euclidean action is defining some classical probability distribution, and this is just a relative entropy with respect to.
That's right. A relative, yes, indeed, a probability distribution over the space of fields, but yes. Exactly. Sure, absolutely. So, okay, so there's going to be 5 parts of this talk. In the first part of the talk, I'm going to review the exact renormalization group and optimal transport. In particular, I suspect that optimal transport may be less familiar to this audience, and so feel free, particularly, to ask questions about that. In the second part of the talk, I'm going to establish the main boxed equation, which I showed you previously, about how renormalization group flow can be cast as an optimal transport gradient flow with respect to this relative entropy. And in part 3 of the talk, I'll show how we can use this formula to derive non-perturbative Rg monotones, and we can compute some examples. In part 4, I'll show how this framework allows us to have a very interesting variational formulation of Rg, namely that by minimizing a certain functional, we can perform a step of Rg flow. And then finally, we'll conclude in part 5 with the discussion. So in part 1, as I said, we'll do a review of the exact renormalization group and optimal transport theory. So let's begin with the exact renormalization group. So let's focus for the moment on the Polchinski equation, again, due to Polchinski in '84, based off of earlier work of Wilson and Kogan and others. So let's consider the case of a Euclidean scalar field with a source. So here we have the partition function for Euclidean scalar field theory, where we have a source J, and we have our usual quadratic action for a massless theory, sorry, a massive theory. And here we have some interaction terms where this might depend on the scale lambda. This is our source. And we have this additional multiplicative kernel. So K lambda inverse just means in momentum space the reciprocal of K sub lambda. So it's literally 1 over K sub lambda, where this is our cutoff function. What our cutoff function does in momentum space is that it cuts off the physics above the scale where p squared goes as lambda squared. So what this does is this renders all correlation functions in the theory as having soft behavior, having a soft cutoff behavior above the momentum scale lambda. So good. And here, let's assume that the source J, for simplicity, we can consider more sophisticated behaviors. Let's assume that the source vanishes above the cutoff scale. So we're only interested in probing correlations below the cutoff scale. So now, Polchinski's basic insight, or a way of phrasing his insight in this paper, is that he says, well, the physics, namely the correlation functions that are below the cutoff scale, are preserved under an infinitesimal step of Rg flow. Namely, if we're only probing correlation functions, if our J is supported below the cutoff scale, then it should be the case that as we change our partition function as a functional of J a little bit with respect to lambda, that what we should get back is something which is proportional to the original partition function. Namely, we should get a partition function which has a proportionality factor that doesn't depend on any of the fields, so that all of the correlation functions of this new object are preserved as long as we compute correlation functions below the cutoff scale. So this is just the statement that below the cutoff scale, that Rg flow, or sufficiently below where we're doing Rg flow, that correlation functions should not be affected. Now, with this, so let's take this equation and let's expand out the left-hand side. If we expand out the left-hand side, this is what we get. And we see that the only place where we don't explicitly know what the dependence is on lambda is in the interaction term by fiat, essentially. Now, Polchinski asks the following almost Jeopardy type question. He asks, is there a functional differential equation for this quantity? Namely, can we understand how the interacting terms change with respect to scale in such a way that this boxed equation, this starred equation, is satisfied? In other words, is there a functional differential equation which this quantity satisfies such that we end up fully satisfying this boxed and starred equation? So Polchinski has an inspired ansatz which does the job. He says, well, we can get this starred equation to work if the manner in which the interaction terms change with respect to scale is in this way, if they satisfy this functional differential equation. So here we have features of the quadratic kernel here, and we have two functional derivatives with respect to the interaction term, and then this bilocal of functional derivatives. And in fact, if you Fourier transform this into position space, it'll actually be localized at a position scale which is 1 over lambda. So in other words, the way in which the interaction terms are changing with respect to scale is in a way which is local in position space, or rather localized in momentum space at scale lambda. So that's some nice intuitive understanding of what this is. Now, so what is this bias? Well, it turns out that one way of conceiving of the Polchinski equation, a way of rewriting it that's helpful in understanding what it means, is as a form of heat flow. So let me rewrite the Polchinski equation in an equivalent way, not in terms of the interaction terms, but in terms of the whole probability functional itself. It's a little bit unwieldy, so let me compress the notation in a suggestive way. If I compress some of the kernels into this big kernel C of lambda, then we can compare the form of this with a convection diffusion equation, where we can associate the time parameter as minus log of lambda. We see that the Polchinski equation, written in this way, is a form of convection diffusion equation. We see here that we have a Laplacian with respect to P of lambda, and here it is in the convection diffusion equation. And then here we have a gradient with respect to a vector field times the probability distribution. The analog of this is here, where now this index contraction with respect to I becomes this integral over momenta. The point is that the Polchinski equation can be thought of as a convection diffusion equation, which instantiates an exact renormalization group flow with respect to a particular scheme, which is prescribed by Polchinski's ansatz. So let me talk now about a more general framework in which Polchinski's equation sits, a more general framework that is for exact renormalization group flow, which is called the Wegner-Morris flow equation. Now, the Wegner-Morris flow equation can be written in this following way, which might look rather different superficially than the Polchinski equation. It actually has a rather different interpretation. So this was based on some ideas by Wegner in '74, but was really refined and written in this form by Morris in the mid-90s, and then really developed maybe between 2000 and 2010. So the interpretation of this equation is that the way in which a probability functional transforms under Rg flow is by inducing a reparametrization of the field phi. That phi essentially gets mapped to a new phi prime, which is related to the old one by an infinitesimal change in scale times this object, psi, which is called the reparametrization kernel. So in other words, this is telling us how phi is being reparametrized, which induces a change in the probability functional with respect to scale that changes it essentially by a reparametrization in the obvious way. We induce a Jacobian here. Now, this is actually quite nice conceptually because it's telling us that, this makes sense that all probability distributions, all continuous probability distributions with the same support are related essentially by reparametrizations. So this gives us, if we have a reparametrization kernel for a particular renormalization group flow of our interest, then we can understand how the probability functional changes in terms of a reparametrization of the field content. Now, we can think about this in terms of a finite dimensional analog as a type of nonlinear vector flow. Here, the analog is that the way that P changes with respect to T, where again, T is associated with minus log lambda, is by this gradient flow by a vector field, where the vector field can actually depend on the probability. So it's a nonlinear vector flow because the vector field that we're flowing with respect to can actually depend on the probability itself. Now, without getting into too many details, I'm going to flash some equations that might be a bit of sensory overload, but don't worry too much about it. The point is that there is a particular form that these reparameterization kernels have, such that that common Rg schemes can be written in this manner. Suffice to say that there's some lingo here, the ERG kernel and the seed action. Don't worry too much about it. But what I want to advertise is that the Polchinski equation is a special case of this equation, that if we decompose this reparameterization kernel into these objects, there's a special choice of these objects for which this precisely reproduces the Polchinski equation. That's the point that I would like to illustrate.
Jordan,
yes.
If I can interrupt, can you give? I mean, I understand what the Polchinski equation says. Can you explain to me what the general statement is supposed to be, in at least conceptually?
Yeah. So the general idea of the Wegner-Morris flow equation can be stated in the following way, that what Rg flow does in the conception of the Wegner-Morris flow equation is that it performs a reparameterization, a functional reparameterization of a probability functional in a way which is localized in momentum space at scale lambda. That we can think in general about a coarse graining or an Rg flow as doing a reparameterization of a probability functional at scale lambda.
So, I mean, I would have said the same words for the Polchinski flow in the sense that, if I'm thinking conceptually of integrating out high energy modes,
right?
The effective action will pick up higher derivative terms, and I would just write them down, parameterize my effective action in terms of the full basis of all possible interaction terms.
Yes.
And then match, do usual matching. What I'm not getting is what is new in their presentation that is different.
Well, what it makes explicit is that, so there's a few things to say about it. One is that it tells you in the Polchinski, so the Polchinski equation also does this exact kind of transformation. This formulation gives us a better understanding of what psi is, like how to actually write the transformation in an explicit way. But the other thing that it allows you to do, which is potentially more interesting, is that, of course, the way that Polchinski discovered his equation is that he made an ansatz, which a very clever ansatz, which happened to work. But what this equation allows you to do is it gives you a much broader class of solutions that Polchinski could have discovered that would have satisfied the constraints that he was interested in. It allows you to basically ansatz a much broader class of solutions to the type of problem that Polchinski had set up. So that's its other value. It reveals how other Rg schemes can basically be written in a similar but related manner to what Polchinski did.
I see. Okay, good, thanks.
So Polchinski's ansatz, as you described it, was specific to the scalar field theory.
Yes.
Do you have examples of solutions to this more general Wegner-Morris framework that are not scalar field theory or different field theories entirely?
Yes. So there's two different axes of generalization. One is thinking about other solutions to the scalar field theory that are not the Polchinski solution, which there are many examples. In fact, some that were originally given by Wilson and Kogut in their paper. But in fact, there's a whole literature that was developed in part by Morris. Morris was one of, I believe, the heroes of the story, in which people did work out in this framework, Polchinski and otherwise, how to solve these kinds of equations for fields with fermions, for gauge theories, also for gravity in at least in some effective field theory sense. So people did work it out. It's just a bit more. I avoided it for the purposes of this talk because it's a bit thorny. I mean, it's not that thorny. It's notationally very overloaded and it's a bit hard to. So this will demonstrate the key points, but it does in fact generalize. Okay, so now for something completely different, but actually not completely different, as we'll see later on, which is that I'm going to now talk about the theory of optimal transport, originally in the Monge formulation. So it's fun in a physics talk to be able to cite a paper from 1781 or a work from 1781. One does not get to do that so often. Works from 1939 are maybe slightly more common. But the idea of optimal transport really goes back to the work of Monge, who was a French mathematician and also an advisor to the French military in a very turbulent phase of their history. And what he was interested in is a problem which can be motivated in a very literally down-to-earth way, which is that suppose that you have mounds of dirt, that you are in a field maybe, and you have many mounds of dirt which are in a certain configuration. And what you desire to do is that you desire to move the dirt around into a new configuration, of mounds of dirt, which is different than the one you initially started with. Well, if you have a certain cost for taking a bit of dirt from here to there across some distance, then what is the optimal way of reconfiguring the dirt so that you expend the least possible energy? That was the question that he was interested in. It has more abstract formulations in terms of moving artillery equipment and so on, or moving cargo from one city to another. But that's the basic question. Now, let me abstract this question.
Is this related to, in CS, they talk about the Earth mover's distance?
Yes, this is the same thing as the Earth mover's distance. That's the, yes. Yes, exactly. It has a few different names. It's also called the Wasserstein distance, as I'll talk about later, the optimal transport distance or the Earth mover distance. But they're all names for the same thing. So I'll get to that later, exactly what the distinction is. There's not really a distinction between the Earth mover distance and what I'm talking about here, but the main difference between different names is often the choice of what the cost function is, namely how you choose to measure the energy expended by moving a mound of earth or dirt from one place to another. But the basic kind of abstraction of this problem is suppose that we have a probability distribution P. So here's a picture of it. And we have another probability distribution Q, which is the thing that we desire to reconfigure our initial probability distribution into. And we have a map T. So in particular, we have initial and final distributions P and Q. We have a transport map, which maps this space X to itself in such a way that the push forward of T acting on P equals Q. So it's asking, how do we reconfigure our space in such a way that we turn this distribution into that distribution? And then we have a cost function, which basically tells us that if we, what is the cost of taking something at one position and moving it to another position? It assigns us the difficulty of moving a bit of dirt from one place to another. And the idea in the Monge formulation, in any case, is to minimize the total cost. So if you put all these ingredients together, then we want to find a map T that satisfies this push forward property, that it maps P into Q. This is the Monge functional. This is the total cost of moving the dirt from configuration P into Q according to the cost function. We would like to find the T satisfying this constraint, which has the minimal value of the Monge function, which has the minimal expended energy in doing so. So this is the basic formulation of the optimal transport problem, which has countless variations. Now, there's another version of the optimal transport problem, which is more convenient for various technical reasons, which is the Kantorovich formulation, which was developed by Kantorovich and various others in the wake of World War II in the late 30s. So again, it has the same ingredients or very similar ingredients. We have initial and final distributions P and Q. And now we have a transport kernel called pi of xy. And the way you should think about the transport kernel is that it tells us the amount of mass from X that we are going to relocate to position Y. That's what pi of xy means. And pi of xy should have the property that it should marginalize to P of X on its first coordinate and marginalize to Q of Y on its second coordinate, so that we transport the mass according to the appropriate initial and final distributions. And we can have a cost function. And the idea of the Kantorovich formulation is to minimize the Kantorovich functional of pi, where this is now the total cost. If we move an amount of mass from X to Y, and this is the cost incurred, we would like to minimize this over viable pi, which have this marginalization property. Now, the reason why this is a more convenient formulation is that it's actually relaxation of the Monge formulation. It turns out, for some technical reasons, I can give you an example, that you can often find solutions to the Kantorovich formulation, which are not solutions in the Monge formulation. An example is that if you have discrete probability distributions, say delta supported distributions, which have supports, which are different, you can't actually solve the Monge formulation, but you can solve the Kantorovich formulation. In any case, in the Kantorovich formulation, there's this distance called the Wasserstein, or the Wasserstein distance, which was in fact due to Kantorovich, was misnamed, which this is the Wasserstein 2 distance, in which the cost function is just taken to be the square of the Euclidean distance between X and Y, where we take an infimum over pi over distributions which marginalize to P and Q on their first and second coordinates. So in other words, the Wasserstein 2 distance is essentially just the minimum value of this functional with a particular choice of the cost function, and then there's an overall square root by convention to make it look like an L2 type distance. So this, in fact, for various historical and technical reasons, is one of the main examples of, this is an example of what's called an optimal transport distance or optimal transport metric. So now let me tell you a story which is less known to physicists, even though we study the heat equation and various other things in the context of statistical mechanics. So let me first tell you a conventional story about heat flow and then tell you a much more modern story about heat flow. So a conventional story about heat flow, which I believe goes back to the mid-19th century, I believe Dirichlet or maybe even Gibbs knew the following story I'm going to tell you, although maybe in slightly different words. If we look at the heat equation, where we look at how the probability function changes, that it's equal to the Laplacian of P, so this is just the heat equation. Let's consider the Dirichlet energy functional of P, which is 1/2 times the gradient squared of P. So you can think about this as capturing something about maybe the kinetic energy, for example, in this circumstance. Now, if the space of probability distributions, let's call it dense of X, which is probability distributions, which are, let's say, C infinity distributions on X, which are greater than or equal to 0 and which are normalized to 1. And then we can look at the tangent space to the space of probability distributions, which are going to be also, C infinity functions, which integrate to 0. The intuitive reason for this is that if you take a probability distribution and you perturb it by an eta, that eta better integrate to 0 so that the probability is conserved. Now, a very natural Riemannian metric you can put on the space of probability distributions is just the L2 metric on its tangent space. This is the simplest thing you could guess. And you can actually show that with respect to this infinite dimensional metric on the space of probability distributions, that the L2 gradient of the Dirichlet energy function is actually equal to minus the Laplacian of P. What this means is that we can regard the heat equation as a gradient flow with respect to the Dirichlet energy. That the way in which the probability distribution changes with respect to time, according to heat flow, is completely governed or is equal to minus the gradient, the L2 gradient of the Dirichlet energy functional. This, in fact, tells us that the Dirichlet energy functional decreases as a function of time. It's a monotone of heat flow, which you can think about as, I suppose, kinetic energy turning into heat. Now, that was known probably mid-19th century, but now let me tell you something that was only actually known 20 years ago. Shockingly, even though what I'm about to tell you seems like it should be something that was known much longer ago, it actually required some pretty sophisticated mathematical developments that rendered it as only being known circa 2001 or maybe the late 90s. Let's consider the differential entropy, S of P, which is minus P log P, where we integrate over X. Now, it's been known since Gibbs that the differential entropy is in fact a monotone of heat flow. But what's surprising, in fact, is that there's a formulation of the heat equation in which the heat equation is completely governed by a gradient of the heat flow. Sorry, by the gradient, rather, of the differential entropy. So let's consider a rather initially unusual looking Riemannian metric on the space of probability distributions. So here's an unusual Riemannian metric where these etas are related to these barred etas are related to the original ones by solving this differential equation, which actually has unique solutions up to shifting by constants, so which doesn't matter because we're taking gradients. So this is an unusual Riemannian metric. Now, it was established by Otto in 2001 that this is somewhat remarkably the infinitesimal version of the Wasserstein 2 distance, or the Wasserstein 2 metric. Totally not obvious that this is in fact the Riemannian infinitesimal version of this sort of global optimization problem that I was showing you earlier, although we'll talk about that in a bit. Perhaps even more remarkably, with respect to this weird metric that's the infinitesimal version of the Wasserstein 2 distance, if you take the gradient with respect to this metric of the differential entropy, you get the Laplacian of P. What this means is that the heat equation is actually that heat flow is a gradient flow with respect to the differential entropy, where it's a gradient flow in the sense of this Wasserstein 2 metric. So again, this is a contemporary understanding of the heat equation, which has had extraordinary consequences in the context of PDE theory. There have been various Fields medals which have been won for it, in particular the work of Cedric Villani, who is one of the experts in this subject. And this way of understanding PDEs or reaction diffusion equations or convection diffusion equations in the language of optimal transport gradient flows has been transformative in probability and PDE theory. So we're going to leverage this more recent technology and try to apply it in the context of Rg flows and see what we learn.
Jordan,
Yes.
just a dumb question, but so the gradient itself depends on P? Because certainly the metric seems to, if I understand.
Yeah, so the way of thinking about it is that when we have a Riemannian metric, it depends on the fiber. So in other words, we have the space of probability distributions, and above each probability distribution, we have a tangent space. So indeed, the probability distribution can depend on where you are in the base space. So that's why it can depend on P.
Okay.
So if you'd like a slightly overloaded, but the implicit notation is that this is the metric at the point P on the base manifold.
I see. Good. Thanks. Yeah.
Sure. Otherwise, maybe it should be, at P-ish would be a better way of saying it. Okay, so what's the flow of logic? So the flow of logic, okay, at some very high level, at the level of syllogisms or transitive property or whatever, is that the Polzinski equation is a type of heat flow. Okay, the heat flow apparently is a type of optimal transport gradient flow with respect to an entropy. That was what at least in finite dimension. So you might guess, if you were going to venture a guess, that maybe the Polzinski equation is an optimal transport gradient flow with respect to a type of entropy. This, in fact, is true. It turns out that kind of completing this type of transitive logic or transitive property is somewhat non-trivial. But just to lay out why you might expect the results that I'm going to show you is because both of these statements are individually true, and in a certain sense, the work that I'm going to share is how to combine them and then how to draw consequences from the equation that we get as a result.
Is your logic flow also some optimal gradient transport in some entropy space?
Yes. Oh, sorry. Is this by logical flow? Man, not that I know of. I thought you meant is this going to be an optimal? Yeah, it's true of this, but not of the logical flow itself. At least that's way above my pay grade. It is. Okay, so now let's talk about Rg as an optimal transport gradient flow. So what we're going to require is a functional generalization of optimal transport. So this is in this recent paper with Simon Rezhnikov. So we have initial and final distributions, now probability functionals, P1 of phi and P2 of phi. We have a transport kernel, which is pi of phi 1, phi 2, which is going to tell us essentially the amount, or rather the, okay, so recall that the in finite dimensions, which just to ground ourselves, is that what the transport kernel told us is how much mass we were taking from a point X to point Y. This is telling us how much functional mass we are taking from phi 1 to phi 2. So it requires some sort of functional generalization of our understanding, but we can make this more precise in a moment. With the feature that it marginalizes on each of its functional dependencies to P1 of phi and P2. We also have a cost function on the space of fields, a very precise one that will be somewhat interesting, which will tell us the amount of cost that's expended by changing one field configuration into another. And our goal is to minimize in the Kantorovich formulation the total energy or cost of this transport. And the analog of our Wasserstein 2 distance is going to be something that looks quite similar. It's just the functional generalization of what we had before. It's the infamy, the infimum of these transport kernels that marginalize to P1 and P2 on each of their inputs, which is going to be multiplied by this L2 distance between field configurations. So you can see this is some type of L2 distance where we have a kernel. And in fact, this is going to be the exact renormalization group kernel, we'll talk about what this means, that appeared in the Wegner-Morris flow equations. So in particular, this ERG kernel is actually like, well, I'll write out in a moment. It's going to be a kernel which is localized in momentum space at scale lambda. So the way you can conceive of this is that it's the cost of transporting one probability, a distribution of a mass distribution of functional probability from one configuration into another, where we're penalizing changing the field configurations that are near scale lambda in momentum space. So it's about transport at scale lambda at the cutoff scale or at the Rg scale. That's what's being penalized by this Wasserstein 2 distance. So the ingredients that we require to state the result is that, well, we have our distribution of interest P of lambda, which is the distribution which we want to Rg flow. We have our background distribution, which we'll talk in a moment. In the case of the Polchinski equation, this is just going to be a free field theory with the same bare mass as our interacting theory. And there's a factor of 2 here for a reason we'll discuss in a moment. And then we have our relative entropy, which, as Mukund asked at the beginning, is just simply classical relative entropy, but functionally upgraded so that it's over phi, integral over phi. And here, this ERG kernel in momentum space is just going to be the one appropriate. It's just basically the propagator. It's just essentially a derivative of the propagator with the cutoff. It's a derivative of the propagator essentially with respect to lambda. This is the regulated propagator where we're regulating modes that are at scale which are greater than lambda. So the result, what we find for the Polchinski equation, is that this, in fact, is equivalent with these ingredients to the Polchinski equation. That this, if you look at the Romanian, the infinitesimal version of this Wasserstein 2 distance that I just showed you, that the result is that this is precisely equivalent to the Polchinski equation. Now, how does this relate to the Wegner-Morris flow equation? Also, maybe pertaining to some of Mukund's remarks earlier. Now, you might say, well, the Wegner-Morris flow equation looked quite different actually from the Polchinski equation. We will see that they are, in this writing, the way in which they are related is extremely simple. In the Polchinski equation, Polchinski chooses this background distribution for a judicious reason that we'll see in a moment, as being essentially e to the minus 2 times the free action. What if we just made this, what if we just made this free action some arbitrary action? We just generalize it to some S hat, which is just some arbitrary action. Well, if you do that, if we call this the seed action in the lingo of the Wegner-Morris flow equation, this is now the Wegner-Morris flow equation. The only difference between the Polchinski equation and the Wegner-Morris flow equation is the choice of Q. The Wegner-Morris flow equation is the Polchinski equation is the Wegner-Morris flow equation for a particular choice of Q, namely Q being having S hat be the action of the free field theory. But the main takeaway of this equation, or words that we can say about it, although we'll say more words in a moment, is that Rg flow is a gradient flow with respect to the relative entropy, where in particular the gradient is computed with respect to this Wasserstein 2 distance. Now let me say some words about this to maybe illuminate some properties of it. So let me first say some differences between this and the finite dimensional heat flow setting, just at some technical level. These are kind of technical remarks. That the Polchinski equation is a reaction diffusion equation. The Wegner-Morris flow is even more general. So in a certain way, one has to generalize the work that Otto did in finite dimensions in various novel ways. There's also, of course, subtleties with the space of probability functionals. And in the derivation of this equation, there's this importance about the positivity of these ERG kernels and its derivatives. These are just kind of technical remarks. Now, okay, so something that maybe to go back for a moment, something that I never really understood about the Polchinski equation is why the heck there is this 2. Why in the Polchinski equation does Polchinski choose for essentially this choice of Q, e to the minus 2 times the free action? That's essentially a choice of Rg scheme, but why is that choice of Rg scheme special or interesting? So let me tell you why. It turns out that in the Polchinski equation, that with that particular choice of Q, it renders the flow of a free massive theory to be this. In the case of a free theory, using the Polchinski conventions, the flow of a free theory is with respect to the Wasserstein 2 gradient of just the differential entropy. What that 2 does is that if you reprocess it in this relative entropy equation, it essentially turns the relative entropy into a differential entropy. The factor of 2 causes cancellations, which allow this equation to be true. In other words, the Polchinski equation, in a certain sense, is the sort of unique Rg scheme, which allows a free massive scalar field theory to flow according to its own differential entropy. That is one way of characterizing what the Polchinski equation is doing, or rather, what its what a choice of conventions affords. So, as I said, the free theory flows according to its own differential entropy. Now, a question at some intuitive level is, what does this flow equation mean? So one thing to say, which we'll make more precise shortly, is that each step of Rg flow comes as close as it can to be a Wasserstein 2 geodesic, while simultaneously maximizing the entropy production as much as possible. And we will unpack that shortly and show that this has very interesting consequences from a numerical point of view. It turns out that there's going to be a variational characterization, which will make this precise, that what happens in the in all of these ERG flow equations is that one step of Rg flow is a step which is a geodesic flow equation in the Wasserstein 2 distance that is sort of the best you can do in the closest you can be to a geodesic, while also trying to maximize the entropy, or rather I should really say minimize the relative entropy as a more precise statement, as much as possible in a precise way. Now the relative entropy, I should say, is needed in general, since the entropy is ill-defined in the continuum. So you might ask, why did the relative entropy make an appearance? Well, the simple reason, for those who are less familiar with the relative entropy, is that if you just look at the discrete entropy of a distribution, if you try to generalize it, look at its functional generalization, or rather not even functional, if you try to look at its continuous generalization, this is what you would get. This doesn't really make sense because there's a dx sitting inside the log. So in a certain sense, this goes all the way back to the 1950s, when people had similar discussions that there's a sense in which the discrete entropy doesn't immediately generalize to the continuum. So something that you can do is that you can look at a different quantity, which is the relative entropy, in which you look at pi log of pi over qi. If you look at its continuous generalization, essentially the dx's cancel, as you might say, and this has a particularly good continuum limit. So you can think about the relative entropy as a proxy for the entropy that just has a good property, that has a good continuum characterization. So the other thing to mention is that the choice of the renormalization group scheme is encoded in the choice of the background distribution, this Q functional, as well as the choice of the ERG kernel, namely the way in which we are choosing the definition of the Wasserstein 2 distance. Okay, so now let me talk about some applications of this. So one of the immediate applications is thinking about Rg monotones. So let's talk about relative entropy as an Rg monotone. Now, something that should be intuitive, maybe at some conceptual level, is that when we do Rg flow, that we might expect that there's some entropy that's increasing. We're coarse graining, we're losing information in a certain way. It seems like there should be some kind of increase of entropy. So a way in which this can be made precise in this particular context is that, in fact, the relative entropy can be shown to be monotonic under Rg flow. For some technical reason, which I can get into if people are interested, it is prudent to subtract off the normalization of Q. In other words, Q is Q you can think of as being a normalized probability distribution. It turns out to look at that it's more prudent for various reasons to look at the unnormalized probability distribution for Q. So we can accommodate for that in this formula by subtracting off log of its partition function. Don't worry so much about that for now, but the point is that we can establish using our formulae that this is in fact, this quantity is in fact an Rg monotone. It's positive under Rg flow because this is changing the scale with respect to coarse graining is what this minus sign means. So this is a non-perturbative argument, which is interesting. Now, the proof of monotonicity actually relies on the positivity of a functional analog of what's called the Fisher information, as well as some features of this exact renormalization group kernel. So the proof is a bit interesting. And there's some subtleties that arise about orders of limits, but they can be handled, and we do so in this paper. Now, let me talk about what this is good for. So in examples, we find that while this monotone is often infinite, its derivatives actually have meaningful finite parts. So in particular, if we even look at its derivative with respect to lambda, it turns out that there is a term here, which is essentially a kind of contact term that arises when you compute this in a pathological formulation, times a function, so this is from contact terms, times a function which is finite. Now, fortunately, the positivity of this quantity means that C1 of lambda is greater than or equal to 0, because we can regard this contact term as a positive but infinite constant, doesn't depend on lambda. So a way of extracting, if you will, a finite Rg monotone out of this is to look at big C1, which is just an antiderivative of C1, which satisfies this equation. And then C1, big C1 of lambda then is a finite Rg monotone. The point is, because there's this multiplicative structure, we can use this to extract out of this a finite Rg monotone that doesn't have divergences. So let me give you some examples to show you what's going on. First, let's do a free scalar field, and we'll talk about an interacting example. For a free scalar field, we can, of course, solve for the flow exactly. So being careful about orders of limits, it turns out that this is the Rg monotone for a free theory. It turns out that if you're careful about this, this quantity is actually divergent for any kernel. This is like this is our cutoff function in momentum space. But not to fret, the derivative is better behaved. If you take the derivative with respect to scale, you end up getting this quantity, which is finite for a large class of kernels. So this is a sense in which the derivative of the Rg monotone is better behaved than the Rg monotone itself, because it can be formally divergent. And I don't just mean divergent because of this delta factor, which is constant, doesn't depend on scale. I mean the actual lambda dependence is itself divergent here, but if you take the derivative, it essentially gets regularized. That divergence goes away. Now for scalar phi-4 theory, okay, so here we can compute the answer to, well, so let's compress some notation to find these functions of lambda. Now, if we compute perturbatively around some initial scale lambda naught and compute to a few loops in perturbation theory, we find that this is the answer that we get for the derivative of the monotone, which can be checked for any small lambda is greater than or equal to 0. Okay, so now, in the last few minutes, let me talk about a variational formulation of Rg. I think that this is quite intriguing and potentially is one of the most interesting applications of this formulation of Rg flow. So let's talk about
Could I just ask very quickly, you switched that slide before. I was just wondering, the F0, F1, and F2, are those all regularized?
No, they're all finite.
They're all on, okay.
Yeah, none of these are regularized, essentially because they're all related. K, if you will, is the cutoff function. So these things have nice properties at large P.
They're all already those derivatives with respect to the cutoff.
Exactly. So in other words, the log of K tilde is not a good quantity, but the derivative is with respect to lambda. Yeah.
A related question, Jordan?
Yes.
There is no feature here which distinguishes dimensions below 4 and 4?
Yeah, that's a good question. Not that we, yeah, that's a good question. It's baked into what these, the answer is I don't know offhand. I hadn't really thought about that so much, because, but the way you would get it is by unpacking the definitions of what these F functions are, because the D dependence is all in here.
Right. But these are just some damping of high energy modes, right? So in Polchinski's language, you have the standard propagator, and then you just some smooth cutoff function K lambda, which basically takes away all the high energy modes.
Exactly. That's exactly right. Yeah. So that's right. Yeah, so I haven't thought so much about the D dependence, but except to say that it's finite for all D.
Mm-hmm.
Yeah, the D dependence would be interesting. I mean, something that would honestly be more interesting to do, which we didn't do, is, well, what if you looked at this, for example, okay, it's a particular case. What if you looked at this near the Wilson-Fisher fixed point, and an epsilon? I mean, I think something interesting would happen there, but we didn't do that calculation. Yeah, so. Okay, so now let's look at this variational formulation of Rg, which is, okay, so let's first go back to finite dimensions to orient ourselves. Suppose that we have a gradient flow equation, which is just d by dt of a vector field is minus the gradient of f of x of t. So one way that you would discretize this is just into steps where your step size is tau. Okay, so this is just like some, finite difference method. Now the variational formulation of this, so just a very simple observation is that a way that you can solve for x of n+1 of tau, namely like the n+1 discrete step, is by looking at the minimization of this function of x, where this depends on the location of the previous step. So this is a variational formulation of a gradient flow, which is used extensively by numerical ODE and PDE people. So there's the application of this to Rg flow is in the following way. So the Wegner-Morris flow tells us that if we want to look at the way that our probability functional at scale lambda naught, our initial cutoff scale, changes as we change the scale by t, that this is related to the original distribution by a functional reparameterization, where I call the reparameterization this script r sub t. Remember, that was the interpretation of the Wegner-Morris flow equation. So now, some useful notation, let's call the reparameterized version of p of lambda by r. Let's just use the superscript r to denote the fact that we've reparameterized it by this functional diffeomorphism. So now the variational formulation of Rg flow can be written in the following way, which we will further simplify, which is that let's write p of lambda minus tau, so Rg flowing from a scale lambda to lambda minus tau phi. So it should approximately for small tau be equal to this reparameterization, where r is given by the minimization to this optimization problem. Namely, we have 1/2 tau times this Wasserstein 2 distance squared plus this relative entropy. Now, maybe going back for a moment, one slide, we see that it has the same form here. We have a distance squared plus the function that we're gradient flowing with respect to. We see that that can show that there's a similar pattern that happens here. Here's our distance squared time plus the relative entropy, which is the thing that we're performing the gradient flow with respect to. And if you can iterate this for multiple time steps tau to basically approximate the Rg flow at times 2 tau, 3 tau, 4 tau, and so on and so forth. Now, what's interesting about this equation is that it's telling us, I want to revisit a statement that I made before we proceed further, which is that this tells us that, well, what is Rg flow? Well, a single step of Rg flow in the sense of this reparameterization is one which is trying to instantiate a geodesic in the Wasserstein 2 distance as well as possible. Namely, it's trying to minimize this geodesic distance, but penalizing for the relative entropy. That's what this minimization doing. It's trying to minimize the Wasserstein 2 distance while also penalizing the size of the relative entropy, which is saying that because of the way that minus signs work, the relative entropy is like related to an entropy with a minus sign. It's like saying with this 1/2 tau factor, minimize the relative entropy as much minimize the Wasserstein 2 distance as much as possible, while also trying to increase the entropy as much as possible according to this, with these particular factors of tau. Now, one inconvenience of this formulation is that if you wanted to do this in practice, well, there's really two nested optimizations here. On the one hand, you have to do this optimization with respect to the reparameterization, but even to compute this argument, you have to compute the Wasserstein 2 distance, which itself is an optimization. So there's two nested optimizations, which makes this inconvenient. What's interesting is that there's an alternative formulation which allows you to get around this in a very nice way. So let f sub tau be a reparameterization, and suppose that we conceive of Rg as a push forward now with respect to this this diffeomorphism on functionals on field configurations. So that if we now look at p at scale lambda minus tau, this is the push forward with respect to f of tau of the original probability functional. Now, it turns out that the variational formulation of Rg flow can be recast in this interesting way, which is that we can solve by a minimization for this functional reparameterization f of tau is the argmin of the Monge functional, which only depends on f, times plus the relative entropy, where we reparameterize our q function by f. This is nice because this is the Monge functional, and this allows us to now only do a single optimization, which is this argument. There's no optimization inside here. Now, what you would want to do is once you find such an f of tau, we would be interested in now sampling from the push forward, because this is the Rg flow distribution. And the way you would sample from the push forward is very simple. First, you sample a phi from the original distribution, and then you would just map the distribution to its reparameterized version under f of tau. And this is equivalent to sampling from the push forward. So push forwards interface very nicely with sampling. So finally, let me mention some potential numerical applications. So it turns out that if we unpack this, let me write it in a particular way, that the previous slide can be written as an expectation value with respect to samples from our initial probability distribution of a certain, what I will call loss function in the parlance of optimization theory or machine learning, which depends on f of tau and its functional derivatives, as well as p of lambda and q of lambda. Now, the reason I write this is that it's natural to parameterize these reparameterizations f in terms of a finite number of parameters theta. And for those of you who are familiar with techniques in machine learning, if theta is differentiable, well, it would be natural to solve for theta. In other words, you would want to perform a minimization, an argument over theta for the loss function as the function of theta, where you are now are going to sample. There should be an expectation value in here where you're sampling with respect to p. Now, the reason to write it in this way is that this is actually amenable to stochastic gradient descent. That this precise form, this precise kind of optimization problem with respect to theta is exactly the sort of thing that you would do in a machine learning problem where you would perform stochastic gradient descent. And the reason that you're able to perform stochastic gradient descent is because of the structure of this expectation value out front, for those who are in the know about that. It turns out that a good ansatz, in fact, really the correct ansatz for this reparameterization, is for it to be a convolutional neural network. It has the right equivariance properties with respect to translations, as well as the right locality properties, in the sense that you want f of theta to be something which is localized in position space, which a convolutional neural net is. I should also mention that there have been many connections over the last 5-10 years, which have been suggested between convolutional neural networks and Rg flow. What I would like to draw your attention to is that in this particular context, this is a completely precise way in which a convolutional neural network actually connects to Rg flow, because this is a systematic connections between Rg flows of conventional quantum field theories and understanding and convolutional neural networks by means of this variational problem. In particular, a convnet really is the right way of thinking about what this reparameterization is. That's just the correct ansatz class. Okay, so now let me conclude with some discussion, and then we can have further discussion thereafter.
Oh, okay, I'll wait.
Okay, great. So we've established that the Polchinski equation, more generally the Wegner-Morris flow equation, is the optimal transport gradient flow of a relative entropy. And this gives Rg flow a surprising information theoretic formulation in terms of optimal transport theory. Now, we've also found a new non-perturbative Rg monotone, which we demonstrated in a few simple examples. We've established a variational characterization of Rg flows, which is amenable to numerical methods, in particular if we look at lattice discretizations of field theory, in which case these sampling methods can be made efficient. Now, I'd like to now conclude with some generalizations and further directions, future directions. So related to Paul's question from earlier, it would be interesting to generalize this story to a richer class of field theories, including with fermions and gauge fields and so on. And this has been done at the level of the Wegner-Morris flow equations or the Polchinski equations by Morris and others in the first decade of the 2000s. But we haven't. It should generalize to what we did, but we have not explicitly done so, except in the case of the scalar field. Another idea is that, well, there's enormous flexibility in the definition of this Rg monotone. This Q functional, which defines our choice of Rg scheme in the relative entropy, this background distribution, can be anything you want it to be. And it appears, at least that for a judicious choice of this Q, that you might actually be able to use this Rg monotone to constrain the signs of couplings. In other words, if you can use this Q to cancel out certain terms in the action of the functional that you're Rg flowing, then you can, it appears like if you do this in a clever enough way, you can use that to actually constrain the signs of couplings in effective field theory. The other idea is to use numerical methods for renormalization group based on the sampling of Wasserstein gradient flows, which was at least suggested in the last part of the talk. And for those who think about continuous Mera as our tensor networks, an idea would be to use reverse gradient flows and ansatz for C-Mera, something which is very well understood in the context of probability theory and numerics, is the how to deal with reverse heat flows, which is in our context would be like, how do you go from the IR to the UV? For those who have thought about tensor networks, it's all about how do you have a good ansatz from going from the IR to the UV? So these methods might be useful in that context. There's some previous work on connections between CMARA and exact renormalization group by Flistley and Parakar. A holographic interpretation would be interesting. How is this interface with our understanding of the emergence of a dimension or dimensions in ADS-CFT? And it would be nice to also have a further information theoretic understanding. I mean, there's been many works over the last 5-10 years which involve the relative entropy in a different manner in the context of Rg flow, including some of the works I've cited here. And it would be interesting to understand what their connection is. I suspect there is a connection in many of these cases with the formulation that I've presented here. So with that in mind, thank you all so much for your attention. Happy to answer any further questions.